So far we talked about sets from the point of view of a mathematician more than a computer scientist. We said what sets are and what operations we could do with it. But what are sets from the point of view of computer scientists? In particular, if we want to do things with sets, if we want to program with sets, how would we represent them? So in order to talk about that, let us change a little bit and talk about another object, another structure, which you're all quite familiar with, called strings, and show how we could use strings to represent sets. So what we're going to talk about in this lecture is strings, kind of a quick reminder what they are and what we could do with them, and how we could represent sets by strings on the computer and do operations with sets using their corresponding strings that we will call characteristic strings. Okay, so first of all, to define strings, we first need the notion of the alphabet. An alphabet is just a bunch of letters or symbols. For example, you could have an English alphabet with its 26, let's say, ignoring the case, lowercase letters. Or in computer science, the alphabet that you're going to see most often is a binary alphabet where you just have letters, so symbols, 0 and 1. And by the way, binary generally means that there are two letters, symbols, and usually symbol 0 and 1. If the alphabet has only one symbol, we call it a unary alphabet. So a string is a sequence of symbols from a given alphabet. So here is where the big difference with the set comes in. Now we are not talking about things that are there or things that are not there. We are talking about the first symbol of a string is this letter. The second letter is maybe something else or maybe the same thing. So it could be that a string has many repeated letters, no problem, especially with something as small as binary alphabet. If we couldn't allow letters to repeat, we would be limited to very few possible strings. Of course, the symbol may or may not appear in a string, but if it appears, it may appear in different places and different number of times, giving us different strings. So when we talk about a string, we will talk about its first symbol, second symbol, third symbol, and so on. And the two strings are the same if their first symbol is the same, second symbol is the same, and so on for all of the symbols in the string. By the way, so here we probably will be talking about first symbol, second symbol, but in some programming languages, the enumeration starts with zeros, so you will be talking about zeros symbol, then first symbols, and so on. Hopefully it will be clear in every case whether we mean 1, 2, 3 or 0, 1, 2 the string. So here are some examples. Sticking with the lowercase English alphabet, we could write mun, M-U-N, as a string. So the string has three symbols. The second symbol is U, first is M, third is N. 1002 is a string of an alphabet of digits 0, 1, and 2. Well, we could also say it's an alphabet of all the digits, but here we're only using 0, 1, and 2. And here the second symbol is a 0 and the third symbol is also a 0, no problem. And in general, if you want to think of kind of a natural situation where you see string, every natural number would be a string over alphabet of digits. Well, usually you wouldn't start a natural number with a 0, but other than that, it's just a string over the alphabet of digits. Usually, except in very rare cases, we will be talking about finite strings. So when I'm going to say string from now on, unless I say otherwise, it's going to be a finite string. And for a finite string, we could say what its length is. The length of a string is just a number of symbols. And the notation for the length of the string is the same as for the cardinality of a set, 2 vertical bars. So for example, the length of string 1 is 3 and the length of the string 1002 is 4. So again, a length counts occurrences of symbols, not how many of a specific symbol occurs on the string. There is one special string which we call an empty string or a null string. This is a string that has a length 0 and it doesn't contain any symbols, any characters in it. Notation for this string is a little bit different between different books and different other materials that you might be reading. Most commonly, probably, it's denoted by the Greek letter lambda, like a L, but sometimes you see it being written using the Greek letter epsilon. So we'll talk, when we're talking about representing sets, about binary string most of all. And binary strings are just letters of the alphabet consisting of two symbols, 0 and 1. So here are some examples of binary strings. Note that the empty string is a binary string. Well, you could have empty string in any alphabet, it doesn't really matter. And the length of the strings, the first one has 7 characters, second one is 4, third one has 0, empty string has length 0, and if you just have one symbol, it's a string of length 1. So now that we have those strings, how do we use them to represent sets? Let's do it with an example. Suppose you have a universe, and in this case, we're only talking about finite universes. Suppose you have a universe A, B, C, D, E. Generally, because it's a set, there is no order. You could have listed the elements as B, then E, then C, then D, then A. Nothing stops you from doing there. But if you're writing it down, chances are you'll write them in some order. And let's just fix this order. We know what it is. In this case, it's A, B, C, D, E. And now we can talk about the first element of the universe, the second element of the universe, and so on. Now, given this universe and the order of elements, we can define what the characteristic string of a set means. This is a binary string of zeros and ones, whose length is the number of symbols in the universe. So here the universe has 5 symbols, so all of our string will have length 5. And it's a characteristic string of a set if for every position in the string it has a 1 if the set has a corresponding element, and it has a 0 if the set does not have a corresponding element. So for example, if we have a set ACD, which has A, does not have B, has C, has D, and does not have E, the corresponding characteristic string will be 1 because it has A, 0 because it doesn't have B, then 1, 1 for C and D, and 0 for E. So the empty set is always string of zeros and universe is string of ones. So why would we want to represent sets using their characteristic strings? Well, indeed, sometimes we don't do that. When our universe, for example, is really huge, it is easier to just list elements of sets if sets contain very few elements of their universe. But if the universe is fairly small, then representing sets by their characteristic strings makes our life a lot easier when we need to do set operations such as unions, intersections, complements, and so on. So let's again see it on an example. So let's, as before, take the universe to be A, B, C, D, E in that order. Let set A be A, C, and D, and let set B contain elements A and B. So here are the characteristic strings for A, 1, 0, 1, 1, 0, and for B it's 1, 1, 0, 0, 0. Now, to take a complement of a set, it is enough to take its characteristic string, go through it, and flip every bit. Change all zeros to ones and change all ones to zeros. If we do it to the set A, then we end up with a string 0, 1, 0, 0, 1. And what it means in terms of characteristic strings, that's a set that contains the second element, B, and the last element, E, and doesn't contain anything else. So this corresponds to a set BE, and you could check that indeed BE is a complement of ACD with the universe that we have. For the union, if we take a union of, say, 2 or more sets, we take their characteristic string, and for every position we check whether at least one string has a 1 in this position. So for example, if we have A and B, both of them have 1 in the first position, so we make our characteristic string of their union a 1. For the second position, B has a 1, so our new string has a 1 again. For the third and fourth position, A has a 1, so again those two will be 1s. But for the last position, neither A nor B have this element, so both of those strings have a 0, so we leave it at 0. So now we got a string 1, 1, 1, 1, 0 corresponding to the set A, B, C, D, and you could check yourself that this is indeed a union of sets A and B. And very similarly, if you're doing intersection, you make characteristic string of the intersection by checking for every position whether at least one of the strings has a 0 in that position. That is, whether at least one of the sets does not have that element. If so, you set it to 0, otherwise you set it to 1. And again, doing it on our A and B, we end up with string 1, 0, 0, 0, 0, which encodes a set containing only the element A. So we talk about strings representing sets, but remember that sets and strings are different types. So if you're given a string in general, and you're not told that this string is a characteristic string of a set, you should view it as something of a very different nature than a set. So in particular for the set, the main operation that you would do with a set is you would check whether a given element is in a set. For a string, you would check what symbol is in a specific position, which is quite a bit different because different positions may have the same symbol, or they may have different symbols, don't know. But in the sets, an element is either there or not, and there are no other choices. Well, okay. A symbol at a given position can be 0 or 1 if it's a binary string and there are no other choices. But still, you could see that this is a very different kind of operation. And also we have other operations with strings that we don't have with sets, and we will talk about them in a few lectures.